Okay, so now that we've gone through one set of titration, strong acid, strong base, let's take a look at another type of reaction. This time, instead of having a strong acid, what if we use a weak acid with a strong base? So think of it this way. I'm going to set up kind of like a similar picture like we did previously. So to have them in front of us, let's take a look at this. Let's write the generic weak acid at water and weak base plus water chemical reaction. So this was back in this 2 videos ago. But we said that if you take a weak acid plus water, that's going to give us an equilibrium with conjugate base plus H3O plus. And because we produce H3O plus, we use a Ka expression. Okay. And if we have a weak base in water, that's going to give us an equilibrium with its conjugate acid plus hydroxide ion. And so we'd have to use a Kb expression for that. Okay. So which of these two reactions will allow us to deal with a weak acid and its strong base? And it turns out it's going to be the second one. And think of it this way. Here's your weak acid, here's your strong base. So we're going to use a second equation to help us out because it has a weak acid in the title and the OH minus is your strong base. Okay, so we need to work with a KB and an OH again, strong base. So for these titrations, the way it's going to be set up, on the left hand side, you're going to have a base, your weak base, and you're going to have water. On the right hand side, you're going to have your weak acid and hydroxide ions, their strong base. Okay. And so we're going to start from the right hand side and try to find where that equilibrium lies. And so that way, when we get to that point, then all we have to do is solve for x. What is that distance to go from the left hand side to meet you to where you've used up all of your materials? Okay, so that's how we're going to handle this. We're going to use the 4-line method, just like we did in the previous video. All right, so here's our next problem. Find the equilibrium concentrations and pH for this mixture using the 4-line method. You've got 200 milliliters of 0.10 molar HNO2. The initial pH is 2.19. And you've got 100 milliliters of 0.10 molar hydroxide, so strong base. Okay. Now, one piece of information, HNO2 is your weak acid, and that actually has a Ka. So that Ka, if we look it up, is 4.5 times 10 to the minus fourth. Okay. All right. So before we do anything, let's try to figure out how many moles of the base and how much moles of the acid we've got. So if we cancel out the liters from HNO2, you have 200 milliliters or 0.2 liters times 0.10 moles of HNO2 over 1 liter. So 0.2 times 0.1 should be 0.02 moles of HNO2. Okay. And if we do the same thing with the base, you've got 100 liters, or 100 milliliters, so 0.1 liter times the concentration was 0.10 moles per liter, and that's hydroxide ion. So that's going to be 0.01. So it looks like, based on where we're at already, you know that the concentration, the amount of hydroxide ion is half the concentration of your base, or half the amount of your acid. Okay, so what I'm going to do is let's set it up as a reaction. Your weak acid is HNO2, so I'm going to put that on the right hand side. Your strong base is hydroxide ion. I'm going to put that on the right hand side. This is in equilibrium with water and the weak conjugate base of the conjugate base of HNO2 would be NO2 minus. Okay. All right, so initially, the initial moles, we know that we've got 0.02 moles of HNO2 and we got 0.01 moles of OH minus. So at completion, the completion moles, how many, what's going to run out? It's going to be your base. Your strong base is going to run out because you've got less of that. Okay, so I'm going to subtract all the base. All right, so we should have no moles of the strong base left over. And so if we subtract 0.02 from 0.01, or 0.01 from 0.02, you're going to be left with 0.01 moles of HNO2. Okay. Now, the only difference is between this problem and what we did previously is that previously we just had water as the reactants and we didn't have to worry about this. Now, you actually do have a conjugate base that you got to worry about. So if everything went down, if the concentration, if we used up 0.01 moles of hydroxide, that means now we've gained 0.01 moles of NO2 minus. So we got to keep that in check on the left hand side. All right, so that being said, now that we know how many moles we have, if we assume completion, what's the completion molarity? Well, keep in mind you have 100 milliliters of base, 200 milliliters of acid, so 200 plus 100 is 300. So if we take the concentration of NO2 minus, which is 0.01 moles, and divide it by 0.300 liters, which is, again, we have 300 milliliters, so 0.3 liters. 0.01 divided by 3 is going to give us 0.033 molar. Okay. All right. Now, if we have, for HNO2, you're going to have the same thing, 0.01 moles divided by 0.3 liters, or 0.033 molar. And for the base, because that you still have none left over, the concentration is still 0. All right, so at equilibrium. Now, again, the last line, the equilibrium. Now we look at these numbers going from left to right. Okay, so the equilibrium molarity, you've got 0.033 for NO2 minus X because it's on the left-hand side. Okay, for HNO2, it'd be 0.033 plus X because it's on the right-hand side. And then for the hydroxide, plus X. All right. Now, so keep in mind, you know that you've got a Ka expression, you've got a Ka number. You on the right hand side, you don't have H3O plus, you have OH minus, so we got to use a Kb. So we need to find that Kb value. So Kb is going to be equal to Kw over Ka, or 1.0 times 10 to the minus 14th, divided by Ka value is 4.5 times 10 to the minus 4th. And so that value should give us 2.22 times 10 to the minus 11. Okay, so now we can set up a Kb expression. Kb is going to be equal to the concentration of HNO2 times the concentration of OH minus divided by the concentration of NO2 minus. Okay, or if we pop in our values, concentration of HNO2 is going to be 0.033 plus X times the concentration of OH minus, which is X, divided by the concentration of NO2, which is going to be 0.033 minus X. And this is all equal to 2.22 times 10 to the minus 11th. Okay. So at this point, we can apply approximations. Okay, so if we apply the approximation, what we're saying is that X is not really going to change. If we take a look at the denominator, 0.033 minus X. If we take a look at the numerator, 0.033 plus X, whatever X is going to be, because look at the Kb value. It's 10 to the minus 11th. whatever X is, it's going to be incredibly small. So it doesn't matter really what X is. It's not going to change those volumes. It's not going to change those concentrations all that much. Okay. So if we apply the approximation, what we're going to say is that the concentrations of HNO2 and its conjugate base are not going to change. So they're still going to be 0.033. Okay. So 0.033 molar times X divided by 0.033, and that's equal to 2.22 times 10 to the minus 11th. Now, look at what happens. We could divide out the 0.033s. Those cancel, okay? And so we're left with X is equal to 2.22 times 10 to the minus 11th. Holy shit! Holy crap! So now we know we didn't even have to take square roots or anything. The concentration of hydroxide ion is equal to 2.22 times 10 to the minus 11th molar. Okay, and so from that, we can also find the concentration of HNO2, which is going to be 0.033 plus X, which 10 to the minus 11th is really still going to be 0.033 molar. And the concentration of nitrous ion, NO2 minus, that's going to be 0.033 minus X. That's not going to change your concentration all that much either, so that's still going to be 0.033 molar. All right, so last thing, let's find the pH. The pH, we can't find directly. We got to find pOH first. So if we find pOH, that's going to be equal to the negative log of the concentration of hydroxide ion, which we know is 2.22 times 10 to the minus 11th. So if we pop that in, pOH, if we take the negative log of that concentration, that gives us 10.65. And so if we solve for pH by taking that value and subtracting it from 14, that should give us a pH of 3.35. Okay. All right. So yeah, we're good. We are good. We found the concentrations of our species and we found the pH. Okay, so let's try this again from a different point in the titration. So same thing, find the equilibrium concentrations and the pH for this mixture using the 4-line method. We still have 200 mils of 0.1 molar nitrous acid, and the initial pH was 2.19. And now we're mixing it with 150 milliliters of 0.10 molar strong base, hydroxide ion. All right. So we're adding about 50 more milliliters of the base, and we're trying to see what happens next. Okay. So keep in mind that when you multiply 0.2 liters times 0.1 molar, that should give you 0.02 moles. Okay. And if we do the same calculation again, 0.150 liters times 0.10 moles per liter, that gives you, that should give you 0.015 moles of the base. Okay. And we know that 200 plus 150, we're looking at 350 milliliters total when we mix them together. Okay. So our equation was this: NO2 minus plus water is an equilibrium with HNO2 and OH minus. All right, so the initial amounts, you've got no moles of NO2 minus, you have 0.02 moles of HNO2, and you have 0.015 moles of hydroxide ion. Okay, now assuming that we go to completion, so we're going to go all the way to the left. We're going to use up all of the hydroxide ion this time, so it's going to be 0 moles left. But 0.02 minus 0.015, we should have about 0.005 moles left of the acid. Okay. Now, since we've used up all the base, that means that we should also form 0.015 moles of NO2 minus as well. Okay. So that's the completion molarity, moles. What about the completion molarity? So if we take 0.015 moles and divide it by 0.350 liters, that gives us 0.0429 molar of NO2. And if we take 0.005 moles and divide it by 0.350 liters, that should give us about 0.0143 molar HNO2. And hydroxide ion is still 0 because we used all that up. All right, so now if we do this from equilibrium, so if we go back to the beginning and now go forward that way from the left-hand side to get to that equilibrium point, we would have 0.0429 molar minus X for the concentration of NO2 minus. We have 0.0143 molar plus X for the concentration of nitrous acid. And then plus X for the concentration of OH minus. All right, so our Kb expression again is going to be the concentration of HNO2 times the concentration of OH minus divided by the concentration of NO2 minus. And this is equal to 2.22 times 10 to the minus 11th. Okay, so what I want to do is pop in my values. So Kb, the value of HNO2 was 0.0143 plus X. Concentration of OH minus is X. And then concentration of NO2 minus is 0.0429 minus X. And that's going to be equal to 2.22 times 10 to the minus 11. All right, so if we apply the approximation and say that whatever X is going to be, it's not going to change our concentrations of HNO2 and the NO2 minus all that much, that means we're going to be left with 0.0143 for the concentration of HNO2 times X for the concentration of OH minus divided by 0.0429 for the concentration of NO2 minus. And so this is going to be equal to 2.22 times 10 to the minus 11th. Or we could rewrite this just a little bit more. Let's get the X by itself. So what I'm going to do is rewrite this and say 0.0143 divided by 0.0429 times X is equal to 2.22 times 10 to the minus 11th. Not minus 1/11th, but 11th. Okay. So now what we're going to do is solve for X. Well, if we do this division, 0.0143 divided by 0.0429, that number actually comes out to be 0.3333. X is equal to 2.22 times 10 to the minus 11th. So if we solve for X by dividing by the 2, X comes out to be 6.66 times 10 to the minus 11th. And so that's your concentration of hydroxide ion at equilibrium. Okay. Now, because X is so small, the concentration of HNO2, which was again 0.0143 plus X is so small, 10 to the minus 11th, that the concentration is going to be around 0.0143 molar. And the concentration of nitrous ion is going to be 0.0429 minus X. And again, X is so small, it's not going to make a dent. So it's still pretty much 0.0429 molar. All right, and finally, to solve for the pH, we know the OH, the concentration of hydroxide ion. So if we take the negative log of the concentration of hydroxide ion, so take our X value and pop it into the POH equation, the POH comes out to be, let me type that in real quick, negative log of 6.66 times 10 to the minus 11th. So the POH comes out to be about 10.18. And then if we take pH, and that's 14 minus POH, So 14 minus our answer, that should give us a value of about 3.82. Okay. So yeah, that's how we do that problem. Let's try another one. Okay. All right, here it is. Find the equilibrium concentrations in pH using the 4-line method. Again, we have 200 milliliters of 0.10 molar of HNO2. And remember that that's 0.02 moles of HNO2. And now we've got 200 milliliters of 0.10 molar hydroxide. So now you're going to have the same amount of acid and base, and the same amount of weak acid and strong base. So again, your equation was this: NO2 minus plus water is an equilibrium to form HNO2 plus OH minus. And initially, the initial moles, you have no moles of NO2 minus, you have 0.02 moles of HNO2, and now you have 0.02 moles of hydroxide. So if we go from products to all the way to reactants, so we go to completion, you're going to have no moles of the hydroxide, no moles of the acid because everything is neutralized, but you're going to have 2.02 moles of NO2 minus. So if we figure out the completion molarity, 200 mils plus 200 mils should give us 400 mils. Okay, so if we take 0.02 moles and divide it by 0.400 liters, okay, that should give us a concentration of 0.05 molar. And it's still going to be 0 molar for HNO2, 0 molar for hydroxide. So that way, at equilibrium, if we go back the other way now, the concentration of NO2 minus is going to be 0.05 minus X plus X for HNO2 plus X for hydroxide. All right, so now we have a Kb expression, which is the concentration of HNO2 times the concentration of hydroxide divided by the concentration of NO2 minus. And so those values, HNO2 is going to be X, OH minus is X, divided by concentration of NO2 minus, which is 0.05 minus X. This is equal to 2.22 times 10 to the minus 11th. All right, so if we apply the assumption, if I apply the approximation, again, X is going to be so small that it's not going to change the concentration of NO2 minus. We're going to get X squared divided by 0.05 is equal to 2.22 times 10 to the minus 11th. So X squared, if we multiply both sides by 0.05, we get 2.22 times 10 to the minus 11th times 0.05. If we take, so that would be 1.11 times 10 to the minus 12. And then if we end up taking the square root of both sides, X would be equal to 1.05 times 10 to the minus 6. And so this is going to be your concentration of hydroxide, which is also going to be your concentration of HNO2 at equilibrium. And the concentration of NO2 minus is going to be 0.05 molar minus X, but X is going to be so small that it's barely going to make a dent into the 0.05. So the concentration is going to be really close to be 0.05 molar. All right. So we could solve for the pH now. We do have the concentration of hydroxide. Let's switch it up a little bit, and let's solve for the concentration of H3O plus. So remember, that's going to be the Kw divided by the concentration of hydroxide. So 1.0 times 10 to the minus 14th divided by concentration of hydroxide, which was 1.05 times 10 to the minus 6. So that concentration should come out to be about 1.0 times 10 to the minus eighth molar. And so the pH, which is the negative log of the concentration of hydronium ion, that's going to be equal to about right at 8. Right on the dot. And so that's kind of how you work a titration. So you start with data, and then you kind of work your way based on the data that you're collecting. All right, so to give a summary of all the pHs that we found, initially, when there was no base added, the pH was 2.19. Halfway, the pH became, 3.35. At 150 milliliters, so we're at 75%, neutralized, the pH went to 3.85. And then at 200 milliliters, when they were both equal, the pH went to 8. And so there it is. So we can, with our information, we can construct a nice titration curve like we're seeing. Okay. And so that's what we're looking at. And we're looking at this line of the weak acid, strong base titration, where you're starting to see an increase, and then we get to the point where we're at equivalence. Okay. Now, there is one other thing I do want to point out. As the Kas get weaker and weaker and weaker and smaller and smaller and smaller, you're going to notice that the pH of these acids are going to be increasing. So on this curve, as you're looking at the Kas, as the pH keeps increasing, we're starting to see more and more weaker acids. Okay. But that's pretty much how you work a weak acid, strong base titration. So next on the list is to look at the opposite. What if we have a strong acid with a weak base?